for your application for university. But good news, I'll be writing it instead.
Are you gonna write bad thing about it?
Oh, I'm gonna write the worst of things I could imagine. You know.
And you'd write it based on?
Oh, just how I feel about you, you know. It's like, Wei is the worst student I've ever encountered. Her attitude in class is,
You have cookies?
oh, this could change my opinion of you. No, I'm writing the reference for half the class, and I think Connell might be doing it for the other half. Based on everything I know about you.
What's it like? I'm bad in your class, I'm good in other classes.
That's bad luck then, I suppose. Don't worry about it though. Right, we have the second half of the physics lesson to do. Waves. Stationary waves. We're in the middle of doing that, weren't we? Yeah. We can see okay? Yeah. So yeah, I'm very busy, and now I'm even more busy because I was asked to do these references yesterday, so I was trying to do some this morning. Managed to get one done, because when I started like 20 minutes ago, the principal came in with a problem. And once the principal has a problem, you have to stop everything you're doing, and really just, anyways, you don't care about that. Okay, so continuing. I think we finished here. Okay, did everybody manage to draw this last time? Yep. Okay. So next now, there's a small problem with this. It looks like from the picture that the wave perfectly fits inside the length of the pipe. It looks like it's perfectly 1/4 of a wave here. In fact, in real life, this wave actually falls a little bit outside. So the length is not actually 1/4. There's a small error. And this error is called the end correction. Now, to be clear, what exactly is the end correction? It's basically, I call it delta L. It's a short distance. It's only maybe like a centimetre. It's not that big. And it's added to the actual length of the pipe. In pipes, the antinode is not formed exactly at the open end. Rather, it's formed a little distance away from it. There's actually no exact formula for how big the end correction should be. You just need to write this, by the way. Okay, this is enough. Yeah. Wei is a peculiar young girl who breaks her pencils in class and wears neither shoes nor socks. Those are like the cheap pencils you get in IKEA. That's only designed to like write down your order. It's not designed for notes.
Open and fiber. Can we get? Is it possible to get a quarter of weight?
For open?
Yeah, open.
Or do you mean closed?
Open.
No, for open you can't. That's the point. That it'll fall a little bit outside.
Only possible for half.
Only possible if both ends are closed, I think. Basically, we can't fit the wave perfectly inside. It kind of falls out at the end a little bit. There's actually no formula to calculate exactly. I mean, there's some formulas to calculate it, but there's no exact formula to calculate it. if you've done this in high school, you might perhaps even remember doing a couple of formulas. I know there's one formula that uses the diameter as a way to calculate the error. But technically speaking, there's no exact formula to calculate this. Yeah. I think that's all, just the first sentence. Okay. Don't particularly think this one's easy. That's not even worth doing. It's stupid. Right. A stationary sound wave is formed in a 17 centimeter pipe, which is closed at one end and open at the other end. So we have a pipe, 17 centimeters, and we use something called, well actually, does anyone know what this is called to make the sound wave? You should know this, yeah, you use this for the piano, don't you, to tune your piano? No, too old fashioned? Yeah. So you take this and you hit it and it makes the sound. What's nice about these tuning forks is it actually says the frequency on the fork. So this one will actually say 500 hertz. Okay. And the first harmonic is formed. So how much of the wave do I fit inside here? For this one it's a quarter, isn't it? Yeah, so I'll draw a quarter wave here. Whoa, okay, that's not quite a quarter wave. Yeah, and it's this is vibrating like this here, making the pipe resonate. And the question is, what is the speed of sound? Okay, well, this is a sound wave. So the speed of the sound wave, we know the formula. What is it?
F
lambda f, yeah. We know the f, it's 500. And if the pipe has a length of 17, then we know the length, we know the wavelength. It's 4L. So that is 2000 L, which is 2000 times 17, which is 30. Stephen, you fool. 0.17 centimeters. Yeah, disgraceful. 340 meters per second is the answer then. This is actually the experiment you would do to calculate the speed of sound. This is the actual experiment. Yeah.
How do you know if it's the first harmonic or like third harmonic?
If it's not given in the question.
Yeah.
I have to double check because in the exam they always tell you which one is formed. But I think in real life, I think the first harmonic is the one that resonates the most intense. The pipe, do you know what I mean by resonates? Kind of vibrates as you can hear the fundamental. I think also the sound might change as well. So like if you moved on to the next one, I don't think it'll resonate as much and it'll make a different sound. I'm not actually sure how, because it's been a very long time since I did this experiment, like really, really long time.
Then why are we doing this?
Huh?
Then why are we doing this?
No, you're not doing this experiment, but you get these types of questions in the exam. This is not one of the experiments. Huh?
When are we doing experiments?
I'm thinking something like next week, perhaps. Because we just need to finish this chapter.
How many experiments are we doing?
4.
Yeah?
Yes.
4?
Who's here?
I can choose?
No, you do all 4.
4.
Yeah. I have to put you into partners too. How many have I got here? 9. So that means somebody will have no partner. So sad. Huh? No, that makes it too easy then. Nah.
But the one person maybe
Unhappy.
You don't want to be this one person.
Yeah.
I'll think who I shall punish by making them by themselves. Yeah. We'll see. Okay. Are we happy with this one? It's not very, very difficult, is it? But it's a standard exam question. Now, the way they make this a little bit harder in the exam, and I wonder if I'll have to make up an example. The way they make this a little bit harder in the exam is they then talk about the end correction. So you notice in my picture, I imagined that the wave perfectly finished at the end, that there was no kind of error at the end. So I'm going to give you another question now, except this time I'm going to make there'll be a little bit of an error, okay? So it's the same deal. We have our tank, and we say it's 17 centimeters, okay? And we have our tuning fork here, and this is 500 hertz. Actually, let me just check something here. Yeah, it's the last one that's like this. Okay, I'll make it kind of similar. Right, so I'll change it a little bit. Will I? Yeah, no, I'll change it a little bit. Oh, I don't even tell you the length. Okay, I'm going to delete the length. Okay, so what I'm going to give you now is I'm going to give you two frequencies that cause this to resonate. Okay, so I'll say the first frequency is, I'll make it similar to this, 1000 hertz. And the reason I'm writing the little tree here is this one is going to be for the third harmonic. So that causes the pipe to resonate. And then here, the fifth harmonic, we'll say 1700. Like that. Okay. And also for this question, this time, instead of asking you for the speed, I'll give you the speed. So the speed of the sound wave is 340 meters per second. So what I want to know is what is the length, but also what is the error here. Okay. Now, I'll let you try for a minute, but before we start, just a quick check. When you're looking at the third harmonic and the fifth harmonic, how much of the wave is in the third and the fifth? Or what is it like? You have it from your table if you flick back. Is it like 3/2 lambda or something? 3/4 lambda? So this one, 3/4 of the wave is in the pipe, and this one here is 5/4 of the wave. Okay. I don't think I tell you the length of the pipe, do I? No, I don't. And I don't care if you find the length of the pipe. What I want you to find is the error. Yeah? Okay. Give this a try. I'll give you a little hint. I have to give you two measurements because this problem will make a simultaneous equation. You'll actually have two unknowns, the length of the pipe and the error in the length of the pipe. So the hard part here is making the two equations. See if you can make them. What equation could you make with this?
We equal x from.
Yeah.
But the V is not changing, right?
Correct. let's just try and make the equation. So if I was to use this one, I should try to use this formula, B equals lambda F. Right, let's see what we know. Do we know the V? We do, at least we know that. Okay. And do we know the F? We do, it's 1000. Now, do we know the lambda? Yeah, when we do this experiment, there's only one thing we can measure, if you think about it. Can we measure the wavelength? No, because we don't actually know really where the wave is. So we can't measure that. Can we measure the error? No, we can't measure that. Can we measure the length of the pipe? Yeah, we can. So if I know the length, can I know the wavelength? Well, let's say there was no error. Let's say this was a perfect measurement. Then we know 3/4 of the wave is equal to the length of the pipe. So we could say that the wavelength would equal 4/3 the length of the pipe. Yeah? But the problem is here. It's not 3/4 of the wave equals the length of the pipe. Rather, it's 3/4 of the wave equals the length of the pipe plus this little extra piece that we don't actually know because it's fallen outside. So that means that lambda is 4/3 L plus this little error here. So here I should have 4/3 L plus delta L. If I repeat this, I will get the next time 340 equals 4/5 L plus delta L 1700. Yeah. Now, you realize your problem has been simplified because how many equations do we have? 2, and how many unknowns? 2. What do you get if you multiply 1000 by 4/3, please? Oh, of course, 1333 L plus 1333 flip. I do this every flipping year. I think I made a mistake with my delta L every flipping time. Let's see. Let me just think. If I multiply that out, the question, if you're wondering what I'm thinking about, is here. I'm not sure if I should have closed my bracket here and put the delta L outside. I think I should have. Yes, I should have. Now, I'll have to explain to you why though. Why it's like this. Before I actually do that, I'm going to fix this. Disgraceful. Right. Does anybody... Pen. There we go. Does anybody know the reason why I'm saying I made a mistake here and I should have closed my brackets, that the delta L is not in the bracket with the L? Well, yeah, but that's what gave me the reason to think I made a mistake earlier. So my question is here, what's the reason for closing the bracket?
Because always started in the private source.
Inside the container. I mean,
No. I'm thinking more of a mathematical reason. Something to do with the error. What I didn't say is this, that the error is the same. It's a constant. It doesn't change for the experiment. So that delta L, you have to add it to your wavelength, the same amount for each wave. It's a constant error. I don't know if you know it from chemistry, but it's called the systematic error. Have you done this word in chemistry? You haven't done the lab? Yeah. Systematic error means the same error each time. So the delta L is a systematic error. So I should not have included it inside. Because if I include it inside, you realize its value changes because you're multiplying it by the 4/3 or the 4/5. So it should be a constant here. Right, so let's fix that, Stephen. 340. I need to write this down so I remember to fix it.
oh, there's none.
Okay, apologies for that. Let's fix that. So that's 340 lambda f. And lambda we said is 4/3 L plus delta L. And then the other one is 340 equals 4/5 L plus delta L 1700. Alright, that's better. The stupid thing is, I do this every single time I make that mistake. Every single time. And I promise you, when we do the worksheet tutorial, I will make this mistake again. Yeah.
That's okay.
It's a Stephen classic. He does it every time. There's two things, one in each semester, that I every time I do it, I make a mistake. It's this one, and then on the lesson we have to do in materials that we did, the proof. Yeah. Every time, every intake, every year. And I don't learn my lesson every time. I refuse to improve. Okay, so if I multiply this out, I have 340 equals 1333 L plus 1000 delta L. And then here I have 340 equals, what's this one here, please?
1360.
1360 L plus 1700 delta L. Now I don't care about finding the L, okay, so what I'll do is I'll just divide this by 1333 and divide this by 1360. So I get 340 over 1333 equals L plus 1000 over 1333 delta L. And here I get 340 over 1700 equals L plus 1700 over, sorry, that should be 1360, and this should be 1360 delta L. Okay, and then I'll minus them. So they cancel. Which one is bigger? The bottom one, obviously. So if I do the bottom minus the top, so 340 over 1360 minus 340 over 1333 equals 1000 over 1333 delta L minus, backwards, 1700 over 1360 minus 1000 over 1333 delta L. So if I just take this and divide it by that, if you complete it on your calculator, I'll have this. Now, I've made up the numbers, so I'm not expecting a kind of sensible answer, but I'm hoping at least it's a small answer. What's wrong? You're looking shocked. Negative? No, negative's fine. Negative just means that we should subtract here. Yeah.
Minus 0.01.
Yeah. And also remember, I just made up the numbers as well, so is it at least a small number?
Yeah.
What is it?
0.010.
So about a centimetre. Yeah.
But it's negative. I thought you were wrong.
But I made up the numbers. My numbers are completely made up.
So it's impossible for it to be
No,
negative?
it could be inside of it. It's usually outside of it. But when you're doing this experiment, I'm sure you see, the problem is, the reason for this is to do with the opening at the top. This is causing the wave not to perfectly finish at the top. So I don't, like, the reason for it is not clear. There's no formula. So it could be that, maybe if you use a beaker that has a curved top, the wave then forms slightly early. It ends slightly early. Or maybe if it has a straight edge. You know what I mean? Like, it's not like there's a clear theory on why the wave actually is outside the top. Huh?
A, B, C. How do you know it's outside?
Oh, because when you do the calculations, you get the delta L is positive. And in this case, because the delta L is negative, it meant that the wave didn't actually finish exactly at the opening. It finished a bit short of it. So you actually got a little bit more of the wave than you thought inside the pipe. Yeah. But no, there isn't actually, the physics for the reason for this error is not clear. So there's actually no formula. The formula, I think there's some formula that says the error should be something like roughly 1/3 of the diameter of the opening. But that's only an estimate. So that kind of seems right. Doesn't it kind of seem like the pipe could be 3 centimeters wide? You know. Okay, did you write this one down? Now, this type of question, I've seen this in the exam twice, maybe 3 times. But this is the thing, I've seen it recently. I don't see it in the old papers. So this is kind of a popular question right now for the exam.
Section E.
No, could be both. No, could be A, yeah. The only reason this took longer was because I had to redo it. But it's really, once you form the equations, it's just a simultaneous problem. But forming the equations can be a little bit hard.
But we always need if it's open. Like if both ends.
Oh yeah, there's always an error when it's open. But most of the time, you don't have to consider the error in the question. You only have to consider it if the question actually says, calculate the error, the end correction, yeah. But a lot of the time in the exam, like say 75% of the time when we have this question, we don't consider the error. We just do the simple V equals lambda F like we did in the last example. But a lot of the, 25% of the time, they'll want you to calculate the end correction.
What if it's an both open ends?
Oh,
The errors you have to calculate.
both open ends, errors on both ends.
We can find it.
Do we just find one because it's constant, or?
I don't think they'll do that because
The area is
they should really keep it closed and open at one end, because if it's open at both ends, then you have 2 errors, which means you have a degree 3. Yeah, because you'll have the length of the length of the pipe, the error on the top, and the error on the bottom. Now the error on the top and the error on the bottom probably will be the same.
Yeah.
But it might not be in real life because it depends on the shape of the openings, you know. But anyways, I know that they won't do this in the exam. I know they won't, because they always do this question where they have a student and the student puts a pipe on the table, so straight away you can't have the bottom open. And then they also, what they do is they fill the pipe up with water, and the reason they do this is so that they can change the length. So it's like that they can make the pipe a smaller pipe. So they use the water to set the length of the pipe. So that's why I was laughing, because I can't imagine them making a question up so that the pipe is open at both ends. So I don't think that's something to worry about.
The wave is finished
At the water.
at the water.
Yeah. Yeah. Now that's another reason for the error too, is that the water isn't going to be a perfectly flat, solid surface, you know. So this is the hardest this lesson gets. It's the error correction, as you can see. Let's have a look at the questions here. So all of these they're all okay. You might think 5 and 6 is too hard for the exam because sometimes I make the last questions quite hard, but in fact both 5 and 6 are questions I have seen in the exam. So all this lesson is exam difficulty. Okay, can you try these for a few minutes and then we'll have the chapter finished? Oh, and by the way, for all the questions, you can take the speed of sound to be 340.
Chord means like string.
Which word?
Chord.
What?
Chord.
Chord. Chord is a musical string.
Dong dong.
No. Bing bing.
Oh.
No. Yeah. It's like the string. Yeah. You know I have to write your reference, don't you? It's a useful word. Wookie is an interesting boy. He makes interesting sounds in class.
Good way.
In a good way, yes.
To understand something.
Yes. He likes to understand things using sound. Yes. Because I have to write your reference, it actually would be good to know what you're applying to, so I can make the reference relevant to that. So I just need the general field. So like it'll be engineering for you of some form. You're actuarial, so I'll have to remember that. You're an astro, so that'd be the physics department of the university rather than engineering. Okay, I'll remember that. What for you?
Actuary.
Oh, yeah, actuary as well. Computers?
Geophysics.
So what department would geophysics be?
Earth and environment.
Environment? Yeah. Okay. I've never written one for environment. You? Engineering? Architecture. Easy peasy. I've done this one before. Computers? The computer department, I could keep it along the lines of computers. I should say he's great at computers and he loves computers. Okay, right.
The sound recently whether 504, 704.
Yeah, it happens regardless of how much the harmonic.
Yeah.
Yeah. And again, just to remind you, it's a systematic error, meaning that in fact the number of the harmonic doesn't actually affect the size of the error. It's a constant. Come in. Oh, the door. Sorry. Great. Thanks. I'm just, Audrey, I'm just looking at some questions here about the error, and I can see, in fact, sometimes in the question they say, neglect the end correction, as in, they're telling you not to consider it. Okay, the question is not as common as I remember it then.
What do you mean indeed? If we make it,
Every time you say leaks, I keep feeling to myself, I perhaps shouldn't have used that word. I should have chosen a different word. Yeah, go on, yeah.
If we make the pipe perfectly the wavelength, will it still leak?
No, but the problem with this experiment is you don't know the wavelength to begin with. You're getting the wavelength from the length of the pipe, and you're getting the length of the pipe by adjusting the length until it resonates, and it won't resonate perfectly at the wavelength. It'll resonate most when the wave is actually a little bit outside of the pipe. So, like, in theory, I suppose if you knew the length of the wavelength, you could set the length of the pipe to be that, and it would fit perfectly in it, and the pipe would resonate. But if you were then to adjust the length slightly, it would resonate more, and then that makes you think, oh, maybe you didn't actually get them matched up, but you did. It's just the maximum resonance happens when the wave is actually slightly, ever so slightly outside the pipe. Yeah. So I suppose the problem is, when we're doing this, we're always working from not knowing the wavelength and only knowing the length of the pipe. And this is how the error gets introduced, because we can't actually set the length to match the wavelength. Because when we think we have it matched, it's actually slightly outside of it, because that's when it resonates. Yeah. And maybe leak isn't the best word. Maybe I should say... Huh? Escapes? No, that makes it sound like it's trying to get away. I need something else. I'll have to think about this now. I'll have to look in a dictionary for an appropriate word. I kind of want a word to say the wave has a tendency to be outside the pipe, the antinode. Like aversion or something.
How to do number
5 is a wonderful question. A car is travelling at 120 kilometres between two radio towers. And as they're travelling between the radio towers, the signal on the radio, it gets a little stronger and a little weaker. What's happening actually is that there's a standing wave formed between the two towers, and each peak of the signal corresponds to antinodes, and each dip in the signal corresponds to nodes. So you could work out the distance between antinodes or nodes, and from that you can know the wavelength, and from that you can know the frequency.
What does it mean by 43 seconds?
Oh, when you're driving in the car, every 43 seconds you reach a peak signal strength.
You mean
An antinode. Yeah.
So the distance between two antinodes is 43 seconds?
Yeah.
I
Yeah.
mean, the radio tower.
Yeah.
It and cars like this.
No, the other way. The radio towers are like this, and the car's going the car's basically going from radio tower A to radio tower B on a straight line. And as it drives, every 43 seconds, there's a peak signal strength. So that means there's an antinode every 43 seconds. Yeah. Yeah. Now remember, if you know the distance between the antinodes, you can know the wavelength. Because we said the wavelength is 2 times that distance. Can we know the distance? Of course we can. It's just how far the car travels in 43 seconds. And if we know the wavelength, and if we know the speed of the radio wave, what is the speed of the radio wave? Speed of light. So if we know the speed of light and the wavelength, we can know the frequency of the wave. Oh, and we usually give this frequency in, I think, kilohertz. You can see what you can get.
symbol for wavelength? Oh,
Lambda.
So we don't have to we use the speed of light instead of the 340.
Do you know why? Yeah. Did you get an answer for number 5?
No, 30 seconds.
Okay, I'm not rushing you, I'm just curious. Did you get an answer? You're in progress? Ah, okay.
I'm not sure which one. What's it called?
Kilohertz?
Yeah.
That numbers
You have an answer?
105 kilohertz.
Sounds about right. There might be a bit of a round in there, but what you got?
104.8 kilohertz.
Yeah. You see, it's depending on how many decimal places you use. So, you know when you're listening to the radio and they say this is FM 104 or FM 105? It's that number. It's the frequency of the station in kilohertz.
FM 0.0.
No, there's never 0 point. It's usually around about 100.
100.
Yeah, so
One.
in Ireland it's, I don't know, between 92 kilohertz and 120 kilohertz.
FM 104 and 105 they produce.
Yeah, that's it, the frequency of the radio tower. When they say they're FM 104 or FM 105, they're saying the frequency of their radio tower is operating at a frequency of 104 kilohertz. Let me just stop the video, there's only recording.